let's go to the next example. Oh, by the way, 44 Tesla is a huge magnetic field strength. There are very few places in the world where you would find a laboratory that has a strength of a magnet that's 44 Tesla. The very strong magnets that you will find, rare earth magnets, will have a strength of something on the order of about 1 Tesla. The magnets that are on your refrigerator are going to be some maybe hundreds or maybe even 1,000 Gauss, which is like 100th or 1/10 of a Tesla. So common magnets that you see in everyday life are going to be something that's less than 1 Tesla in strength. 44 Tesla is a huge magnetic field strength. Next example. An electron travels at 2 × 10⁷ meters per second to the right as it enters a 0.01 Tesla magnetic field directed into the plane of the page as shown. A. Determine the magnitude of the force acting on the charge. B. Determine the direction of the force as it enters the magnetic field. And C. Sketch the magnetic field and the path that the charge takes. Describe the path as either moving clockwise or counterclockwise. I want to take the direction part of this problem first and then do the calculation at a moment later. We are now dealing with a negative charge, an electron. And in this case, we want to apply what is called the left-hand rule for the Lorentz force on a charge moving in a magnetic field. Fortunately, the anatomy is the same as the right-hand rule. So again, we're going to let the direction of the fingers of our left hand be in the direction of the velocity. We're going to let the direction of our open palm be the direction of the magnetic field. And then the thumb of our left hand will give the direction of the force on the negative charge. So in this case, I'm going to take my left hand. I'm going to extend the fingers of my left hand towards the right. I'm going to have my open palm face down on the page. And the thumb of my left hand points in the downward direction. So again, think of this rectangular space as the place where the magnetic field is confined. Let's sketch those 3 vectors in the magnetic field as we did in the previous problem. The velocity is to the right. The magnetic field is into the page. So the force as the particle enters the magnetic field is going to be downward. Now, of course, this force is perpendicular to the velocity. So the magnetic force is going to be a centripetal force tending to cause circular motion of the particle as it enters the magnetic field. So this particle is going to change its direction as it goes into the magnetic field. And its trajectory is going to look something like this. Since the trajectory pushes the particle downward as the particle moves to the right, then what we see is this appears to be clockwise motion in this magnetic field. So now we've answered part B. The direction of the force as the particle enters the field is downward. Part C, we are sketching the path and describing it as clockwise motion. Now what remains is that we actually figure out what is the strength of the force. So let's apply the Lorentz formula again. F is equal to QV cross B, which means that the magnitude of F is equal to Q times the magnitude of V times the magnitude of B times the sine of the angle between V and B. In this problem, as in probably more than 90% of the problems you're going to work involving magnetic fields and charges moving in them, the direction between the velocity vector and the magnetic field vector, that angle is going to be 90 degrees. That means that the sine of the angle is going to be equal to 1. And you can say that the force is equal to Q times V times B. So now let's put in the numbers. We have an electron. The charge on the electron is the same in magnitude as the charge on the proton. The elementary charge, 1.6 times 10 to the minus 19 coulombs. Put that in your calculator, and out pops a number. I find the strength of the force acting on this electron moving in this magnetic field is 3.2 times 10 to the minus 14 newtons. One more numerical example. And in this one, I have modified the problem statement. I've actually added something. A charge of 8.1 times 10 to the minus 9 coulombs enters a magnetic field with a speed of 2.2 times 10 to the third meters at an angle of negative 30 degrees as shown below. The strength of the field is 4 Tesla and is directed left to right across the plane of the paper. A. Determine the magnitude of the force the magnetic field exerts on the charge. B. Describe the motion of the charge in the magnetic field. assume that the charge does not escape the magnetic field once it's trapped by it. Okay, so let's solve the numerical part first and then describe the motion. Now, in this particular problem, the direction of the velocity and the direction of the magnetic field are not perpendicular. There's an angle between them, and that angle is 30 degrees according to this problem. Let's write the Lorentz force. F is equal to Q times V cross B. In magnitudes, F is equal to Q times the magnitude of V times the magnitude of B times the sine of the angle between V and B. I know all these numbers. Let me put them in. And now, put them into my calculator and come up with a result. I find that the strength of the force, the magnetic force on this moving charge in this magnetic field is 3.6 times 10 to the minus 5 newtons. Now, let's talk about the direction of the force. In this case, what happens is that the velocity and the magnetic field are not perpendicular to each other. This is a positive charge, and so I'm going to use my right hand, and I'm going to see that when I place my right hand fingers along the direction of V and my open palm in the direction of the magnetic field, then what I get is that my force is going to be at some angle with respect to the magnetic field. There's going to be a piece of the force that's perpendicular to the field and a piece of the force that's parallel to the field. Let me see if I can sketch this down below here, and then let's see what happens. Because what we're going to see is that this charge would spiral in this magnetic field and form a helical sort of shape around the magnetic field lines. That's what the trajectory is going to look like. We're going to see that the one piece of the force is directed out of the page, but there's also a piece of the force that's parallel to the magnetic field. I'm going to try to sketch this in 3 dimensions, a helical sort of trajectory as the particle enters the field. If the particle is trapped by the magnetic field, then it will go in a helical path around the magnetic field lines. If you're lucky enough, someday you may see this in person, and it's a beautiful sight to behold. And in fact, if you go to the polar regions of the Earth, you can actually see this. It's a very beautiful sight. It's called the Northern Lights, the Aurora Borealis, or you may see it in Australia as the Southern Lights, the Aurora Australis. When this happens, these charged particles coming from the sun get trapped by the Earth's magnetic field lines. They spiral around the lines, colliding with air molecules, and the nitrogen and oxygen excited electrons then, when they fall back down into their ground state, give off very beautiful colors of light. So now I leave you with some images. And these are images of auroras. These are Aurora Borealis. You can also find images of Aurora Australis. Very beautiful, very colorful. I find them to be highly satisfying, and it's an exciting thing if you ever find yourself in the northern hemisphere close to a pole or the southern hemisphere closer to the pole during what they call a solar storm, and finding these beautiful charged particles trapped in the Earth's magnetic field producing these lights. They're a result of the Lorentz force trapping charged particles and those particles colliding with air molecules. So for now, that's it.